All right, so let's go ahead and start talking about the initial observations of Sherrington and why we think that synapses are chemical in nature. So I just want to give everybody again like the context for what it is that we're talking about, because when we start talking about biology and the strict nature of it, I think that people's eyes start to glaze over a little bit. We start to not pay attention because it's boring. So, trying to remember what it is that we're actually talking about can be very important and helpful. So, we have nerves that are in our sensory organs, our eyes, our tongue, our nose, and they are communicating information to us that they are picking up about the outside world. Photons are bouncing off of the water. The sugar molecule is binding to your sweet taste receptor. The odorants that are being released from the flower are binding to the glomeruli that's in your nose that are talking to your olfactory bulb that's then, traveling through your peripheral nervous system to then talk to your central nervous system and then give you a perceptual event. Okay? So, how though are these neurons talking to each other? How do they communicate? We know that within a cell, that's an electrical discharge that arises, from the integration zone at the soma, travels down the axon, and then results in something happening at the terminal button, right? So what's happening here? What's actually happening? Well, I'm gonna plug this in. Is the release of chemicals. For the vast majority of synapses, it is a chemical event. There are some electrical synapses where it's just one neuron releasing an electrical discharge directly into another neuron. But for most synapses, it's a chemical event. So again, here we have the presynaptic cell, and here we have the postsynaptic cell. I spoiled it. Yeah, so here's the chemical. How do neurons communicate? Chemically. That's how they do it, right? So anyways, what is a synapse? The synapse is the gap between two neurons at which they communicate chemically. So, if you progress in any biological psychology course, neuroscience course, psychopharmacology, any of those, you're going to see this diagram in some shape or form about 50,000 times. This is a presynaptic cell. This is a postsynaptic cell. It's called a presynaptic cell because it is the neuron that's doing the communicating. It's before the synapse. This one is the postsynaptic cell because it's the neuron that's being communicated to, and it's after the synapse. So we've zoomed in on a terminal button, and here we've zoomed in on a dendrite or dendritic spine of some sort, and here are some receptors, and then here are the vesicles that contain neurotransmitter. So, this is Charles Scott Sherrington, and he, was a neurophysiologist from 1857 to 1952. And although, maybe actually I should, instead of covering his face, maybe I should go underneath his chin. In any case, Sherrington was a neurophysiologist, and just know, I know that I've put the dates on all of these figures. I'm not going to ask you any history questions about the dates. You know what I mean? I'm not going to say when was Sherrington a thing. I just want you guys to, have an appreciation for when these observations were made, because honestly, we're in 2025, but my dad was born in 1950. So, what we know about modern neuroscience, actually there's like kind of a lot discovered in the 19th century, which was not very long ago. So, Sherrington used behavioral measurements to infer properties about the synapse. He used reflex arcs to primarily look at potential information about synapses in dogs. And a reflex is an automatic muscular response to a stimulus. So that's the context that we're going to be using. And Sherrington observed that there was a delay between pinching a dog's foot and seeing the dog raising that foot, which infers something weird is going on here because electrical communication is extremely rapid, right? So if there's a delay between pinching the dog and the dog having an automatic reflex, then that infers something interesting is happening um, between the nerves that are communicating. So he also observed that if you disconnect the spinal cord from the brain, he saw the same reflex, which means that the extension and the flexion of the response, meaning that when the dog, or anybody, when you have a reflex that results in your limb going away from you, that's the extension. The limb coming back is the flexion. But in any case, the fact that you could sever the spine from the brain and still get the reflex means that it's a peripheral nervous system response. It's something that's happening at the spine. And he actually found, this part was really cool. When severing the connection between the spine and the brain, the reflex happened even faster. So although the reflex is something that is occurring at the level of the spine, it is being modulated in some way by the brain. So he made 3 observations that we're going to focus on in this lecture that you're going to have to know. 1, reflexes are slower than conduction along an axon. 2, several weak stimuli presented at nearby places or times combine their effects. And 3, when one set of muscles becomes excited, a different set becomes relaxed. And since that is the case, we need to have some kind of explanation for how that's possible. So, for the first observation, reflexes are slower than conduction along an axon. When he pinched a dog's leg, the dog would reflexively kick the leg back, and he measured how long the distance from the leg to the spine and the brain was, and he approximated that the signal must be traveling about 15 meters per second, which is contradictory to how fast the electrical discharge of an axon is. So the electrical traveling through the neuron is 40 meters per second. So why is it that we're only observing 15 meters per second when we're actually looking at the reflex? And again, the 15 meters per second is that's how much he thinks that's how long it's taking for the signal to get to the brain and come back to cause the leg to kick. Okay, so that's where he's coming up with this. He literally took some measuring tape, or I don't know what the heck they had, but he measured how the distance of the dog's body, right? That's what he's doing. And so that's how he's coming up with his number. So he hypothesized that it may be that the electrical signal traveling through the neuron is very fast, but maybe the neuron to neuron communication is slow. Okay, so he's saying, it's going 40 meters per second within the cell, within the neuron, but maybe once we get to this connection between two cells, that's where it's slowing down. So his second observation was that several weak stimuli presented at nearby places or times combine their effects. So if you just pinch the dog's leg, you obviously get the dog to kick. However, if you touch the dog's leg and you don't quite pinch it, so you're giving a sub-threshold stimuli, or a stimulus that does not reach the threshold to cause the reflex, the dog will also kick if you do it enough times in the same spot. Or if you do it fast enough, or if you do it at multiple different locations, then you get this reflex arc, even though it was not in of itself a strong enough stimulus to cause it. And this is called temporal summation. So unfortunately, we do have to go back to the little graphics that talk about action potentials. So here you should be pretty familiar after the last couple lectures about what an action potential looks like when it's graphed. So here is a pretty clear representation of 2 action potentials occurring. So let's go ahead and first, in order to understand temporal summation, we have to understand what an EPSP is. So EPSPs are excitatory postsynaptic potentials, and as we discussed in the lecture on action potentials, what an actual action potential is when a neuron is getting a chemical signal that results in the influx or efflux of ions, right? So we get it. I'm sorry, I kind of said that a little bit wrong, but it's because I'm trying to read it and also talk. So let me just see what I wrote here. Is when neurons are getting, so as we discussed in lecture on action potentials, EC, okay, so I just wrote this weird because I don't know how to write. So let's just skip this superfluous text here. Excitatory postsynaptic potentials are when neurons are getting chemical signals that result in the influx or efflux of ions. So that will result ultimately in an action potential, right? So here we can see this EPSP, which is an excitatory postsynaptic potential. And again, it's called this because it's causing an increase in the membrane voltage. So that's why it's excitatory. And then it's a postsynaptic potential because this increase in voltage is occurring on the postsynaptic neuron. All right. So here we can see a little bump in the voltage of the membrane, and that's due to some kind of neurotransmitter release that's opened up an ion channel that's resulting in the influx of, a positive ion. And then if we get enough of this, then we're going to get the action potential. So if we look at this, this is kind of just giving you guys a little refresher on the action potential. We get to the threshold, sodium channels open. This causes a rapid depolarization of the membrane. The potassium channels open, causing a massive efflux of potassium, resulting in the falling phase. And then the sodium-potassium pump restores the membrane to its resting potential. So that's the action potential occurring. And these EPSPs are the small little bumps in membrane voltage that's occurring that's going to eventually get us to the threshold if it happens fast enough. So let's see what I wrote here. If the neuron is getting excitatory signals, this is typically indicating that there is an influx of sodium. That's for sure going to be a test question. An EPSP is referring to the excitatory signals that the postsynaptic neuron is receiving that will elicit an action potential if the threshold of the voltage-gated sodium channels are reached. If there are enough of these sub-threshold EPSPs in short enough amount of time, the neuron will have an action potential. This is the demonstration of the principle of temporal summation. Yeah, so let me go ahead and try to explain that again in a different way. What I'm saying here is that excitatory postsynaptic potentials are the sub-threshold excitation that occurs that will lead to an action potential if enough of them happen in rapid succession. And that's temporal summation. Temporal has to do with time. So if you have enough of these sub-threshold excitatory events in a short enough period of time, then the membrane is going to reach the threshold that results in an action potential. So a part of temporal summation, though, is also the inhibitory. What is that word? It's also part of the inhibitory balance that is a part of an action potential, right? So IPSBs, as you might expect, are the opposite of an excitatory postsynaptic potential. An IPSB is an inhibitory postsynaptic potential. And this is when neurons receive inhibitory signals that open chloride channels. And since chloride is an anion, this results in the neuron becoming more negative and hyperpolarizing the cell. Exactly. In the diagram above, the IPSPs are shown after the action potential has transpired, but realistically, neurons are always receiving a combination of inhibitory and excitatory signals. If there are more IPSPs, or if the IPSPs are stronger than the excitatory signaling, the neuron will remain polarized and at a resting state, right? So I put the IPSPs in with the temporal summation because if you remember again, when we talked about action potentials, we have like this integration zone, right? That's in the soma, that's going to kind of make a decision. Do I fire? Do I not fire? And that's dependent upon whether or not the membrane has reached a certain voltage. And so it's taking in all of this information that is EPSP, so excitatory postsynaptic potentials, resulting in an influx of sodium, as well as IPSPs, which is an inhibitory postsynaptic potential that's resulting in the influx of chloride. So for sure, I will ask, what's the main ion associated with an IPSP? It's chloride. What's the main ion associated with an EPSP? It's sodium. So those are for sure going to be test questions. So just make sure you're aware of that. So again, hopefully my painful meandering around this topic is not too confusing. Temporal summation is just the concept that a nerve cell is taking in all of the relevant information in a short period of time and deciding whether or not it's going to fire an action potential, and that decision is based on its membrane's voltage, right? So if a neuron fails to fire, that's a result of temporal summation. If a neuron fires, that's a result of temporal summation. So I think that that's a little bit more complex than what the textbooks like to talk about, but I just want you guys to understand that temporal summation is not simply just an action potential, okay? So what's spatial summation? Well, if temporal summation has to do with time, then spatial summation has to do with physical space. Temporal summation is the concept that a certain number of subthreshold signals can produce an action potential if there are enough of them in a short enough period of time. Yeah, so that's what temporal summation is. Spatial summation is also illustrating this concept, except it is indicating that you can have multiple different nerves signaling to the postsynaptic cell to produce an action potential at the same time, but different locations, and still end up with the same outcome. Yeah. So there are many ways that you can result in, getting an action potential. One of them is with this temporal summation, if we're talking about excitatory signaling, where you have one neuron that's blasting the postsynaptic cell with enough excitation in a short period of time that results in an action potential. You could also get a similar effect with spatial summation, where you have multiple different neurons all giving excitatory signals resulting in the action potential. So here is that kind of summed up for you. This is temporal summation. We have one neuron QQing a bunch of neurotransmitter that's going to open up sodium channels and ultimately get the neuron to fire an action potential in a short period of time. And then we have spatial summation, where we have these three neurons all sending excitatory signals that will result in an action potential because of just the onslaught from different angles, resulting in an increase in membrane voltage. Was my head covering this? It was a little bit. Sorry about that. Okay, so let's go ahead and look at putting all of this together. I've already kind of alluded to this, and so it's kind of repetitive. So if you already get it, then you can fast forward to the third observation. But basically, this is kind of like, to make it simple, whenever we're talking about action potentials, we always make things really isolated. But realistically, what's happening when we get neurons firing is you're getting all of this happening at the same time. You're getting concepts of temporal summation and concepts of spatial summation, and excitatory postsynaptic signaling and inhibitory signals are all happening to ultimately result in a neuron either firing or not firing an action potential. So let's go ahead and look at an example where the neuron does fire an action potential. We have one neuron up here that's sending some kind of inhibitory neurotransmitter, and we know that because we're looking at this curve of voltage and it's going down. This is an inward current, and what it means is that the neuron is becoming more polarized. But then down here, we have some neurons that are sending excitatory signals, and we know that because their voltage curve is going up. So this is an outward current, meaning that's an excitatory signal. And we have, this neuron is firing really fast. This neuron is firing slow, same as this one. So we have both temporal and spatial summation working in concert with both excitatory and inhibitory signaling. And since we have more excitatory signaling here, we ultimately get action potentials over here. Okay. So I know that that's all pretty complex. If people are confused about that, I'm happy to meet during, like set up some office hours and let's go over it, because I know that it's complicated. It's tough to kind of wrap your head around a lot of this voltage. And if it's super easy for you and it's not complicated for you, then that's totally great. Anyway, so let's go ahead and move on to Sherrington's third observation here, which is that when one set of muscles becomes excited, a different set becomes relaxed. So let's just go ahead and define some, physiological terms real quick with musculature. We have a flexor muscle, which draws extremities toward the trunk. We have extensor muscles, which move extremities away from the body. So let me just go ahead and just take a minute to try and demonstrate this a little bit. If you're in the gym, right? If you're a gym bro or a gym lady, you are familiar with a push and pull day, right? I mean, we have, push days would be like doing a bench press, doing a shoulder press, doing chest and shoulders are typically thought of as your push days. Pull days are doing like pull-ups or bent over rows, or certainly there's more than that, but I can't think of them right now. But in any case, realistically, what's actually happening when you're doing a bicep curl, which might be on your pull day, or a tricep extension, which may be on your push day, all muscles are actually pulling your skeleton towards wherever that muscle is oriented. So you have flexor muscles, which again, as this is talking about right here, is going to draw extremities toward the trunk. So my extensor, or my flexor muscle, I think I said extensor, but I meant to say flexor, my bad. So my flexor muscle here is my bicep, and it's pulling on my arm to result in this limb coming towards my body. My extensor muscle is my tricep here, and it is also kind of unintuitively pulling to extend my arm. So for the gym people, I'm just letting you know that nobody cares, so don't go and tell all your gym friends that actually all days are pull days, because that's annoying. But I'm just saying, though, that it is the case that all of your skeletal muscle is pulling, but it's divided up into these extensor and flexor muscles, and they're so defined because of what direction your arm or your limb is going, right? So Sherrington observed that when activating the dog's flexors through the reflex arc, the dog's extensor muscles would be simultaneously inhibited, or they would relax. This makes sense because you can't do a bench press in a bent over row, right? So it's like, in order for you to be able to do a bench press, you can't have your lats pulling against your pecs that are, pulling your arms together to make the bench happen, right? Like you can't have that occur. So, let's see what I wrote. If you have opposing muscle groups in the same limb, how do they work in concert with one another? Yeah, so gym rats might know this as reciprocal inhibition. Yeah, so if you go on to be a kinesiologist or whatever, and you are taking the NASM exam to be a personal trainer, reciprocal inhibition is a word or a term that you'll be familiar with. So there must be a mechanism that produces inhibition when the opposing system is excited. And because this is the case, this made Sherrington, think that it can't be simply that there's just one neuron that's communicating electrically to the brain and then one neuron going back. There must be a system of neurons, which is what we're going to look here in this reflex arc. We can see that we have the skin and we have nerves that are attached to the skin, and they're going up into the peripheral nervous system, into the spinal column. That's like what this is looking at. It's communicating with the brain. It is then exciting let's see, this little travel here. So this is the inhibitory one, this is the excitatory one. So you're going to have two pathways. One of the pathways is excitatory, and if we travel down here, it is causing the extensor muscle to contract, and simultaneously we have an inhibitory signal that is going to this muscle here and causing the relaxation of this muscle, allowing the leg to flex in that reflex arc. So, this is the knee, and this is looking at that common reflex that you're used to seeing doctors like hit your knee with that little rubber hammer thing. And basically, in order for that to happen, you need to be able to, in that case, it'd be like a leg extension, right? So you need to be able to contract your quadricep and inhibit your hamstring. So, so this insinuates that there is a chain of neurons that are both communicating different information. So these are Sherrington's observations. Make sure that you know those. So what are Sherrington's 3 observations that he inferred the synapse from? What is an EPSP? That's an excitatory postsynaptic potential. What ion is associated with EPSP? Sodium. What is an IPSP? It's an inhibitory postsynaptic potential. What ion is associated with an IPSP? That's chloride. What is temporal summation? That's the idea that the neuron is integrating information from a variety of signals, and if it all happens fast enough, let me see if I can put that more succinctly. It is summing the activity that's occurring over a certain period of time, whereas spatial summation is summing the activity that's happening over different locations, okay? So why did Sherrington hypothesize the existence of an inhibitory synapse? Yeah, so that's what this is here, is that, before this, there was actually, I should have said this and I forgot to, but basically people did not know that inhibitory synapses existed. So when Sherrington pointed out that, you need a way to inhibit the opposing muscle group, it was kind of a radical idea, which resulted in this. So why does he, let's see here, whoops, let me move myself again. Let's see what the question is. Why does Sherrington hypothesize the existence of an inhibitory synapse? Because there needs to be some explanation for how extensor and flexor muscles can work in concert to result in a limb moving properly. That's why. That's the answer to that question, in case it's kind of confusing. Okay, so another kind of short lecture, but kind of in-depth lecture, so make sure to, spend some time on that if it doesn't make sense, and set up some office hours with me if you're really struggling. And we will see you in the next one, where we go over the chemical events at the synapse.